I'm Baby Ninja. I love organic chemistry, and you can too. Hey there, OChemNinjas. In this video, we're going to learn how to turn line angle structures into Newman projections. Being able to take a molecule and look at it from different perspectives is a very important skill in organic chemistry. Viewing a molecule from a different perspective often gives us new information about the molecule, and sometimes reactions only work when a molecule is in a very specific orientation, and changing our perspective can show us whether or not that molecule fits that orientation. One of the most common perspective drawings for acyclic molecules is the Newman projection. Let's get to work. The first thing to say about the Newman projection or any perspective drawing system is that the only thing we can change is our perspective of the molecule. We cannot change the molecule. We cannot break any bonds or form any new bonds. All we can do is change the orientation with which we are looking at the same molecule. When we're done, the molecule needs to be identical, just looked at from a different perspective. Perspective drawings are different than bond rotations. I have a separate playlist on bond rotations that I'll link to down below. With bond rotations, we're keeping the molecule in the same orientation, we're just rotating around certain bonds in the molecule. With perspective drawings, we are completely changing our orientation of the molecule, but keeping the molecule otherwise identical. The way we change our perspective for a Newman projection is we turn our body and we look at the molecule from the side straight down one of the bonds. We're so used to looking at molecules straight on where we see the molecule flat across the screen. The Newman projection changes that, puts our head in the plane of the screen, and we look down the bond as if we were inside, in line with the screen. The Newman projection is the continuation of the Sawhorse projection. If you haven't seen the video on the Sawhorse projection, you should watch that. It's linked down below. If you're not familiar with the Sawhorse projection, I have that video that I'll link to down below. With the Sawhorse projection, we take our molecule and we turn it 45 degrees toward you as the viewer, looking down like a sawhorse. That gives us some perspective on the front and the back carbons in this molecule. The Newman projection takes our molecule, rotates it through the 45 degrees of the sawhorse all the way 90 degrees so that it's completely turned towards you as the viewer. The first thing we need to do then to draw a Newman projection is to look at the molecule from the side. We could do this from either direction. We could look at it from one side or the other side. Both would give valid Newman projections. It's just a matter of perspective. By convention, we look at the molecule from the left side, but there's nothing to say that has to be the way to do it, and there's nothing wrong with looking at the molecule from the right side. So to do the Newman projection, you have to get in line with the molecule and look at it from the side. That's one of the reasons why I really like this light board technology. It really lets me feel like I'm getting three-dimensional and I'm looking down that bond. Some things are closer to you as a viewer, some things are further away from you as a viewer, and that's going to be really important when we draw our Newman projection. In fact, the way to think about this is like my daughter. This is my daughter when she was about 3 months old, and we always noticed that when she was taking a bottle, she was always looking directly ahead of her, just like she would be down a Newman projection. So one day I put a molecule in front of her and snapped a picture. But notice her eyes. Her eyes are in line with that bond, looking right down that bond, just like your eyes need to be right in line with the bond, looking directly down the bond of the molecule to draw the Newman projection. So if I can line myself up with Baby Ninja, I'm going to reorient my perspective so I'm looking directly down this bond as the viewer. My eye is perfectly in line with this bond in the molecule. I would recommend drawing the little eyeball guy so that you can see exactly where your eyeball is pointing as you look at the molecule from a new perspective. And again, there would be nothing wrong with doing this from the other side of the molecule. Both are legitimate ways to draw a Newman projection. Once you have settled on your new perspective, it's time to start drawing the actual Newman projection. So let's figure out what that actually means. We start off by drawing a dot and a disk. This represents our change in perspective from looking at the molecule straight on to looking at it sideways. This dot in the center is this first carbon atom of the bond. This represents changing our perspective. Instead of looking at the molecule straight on, we are now looking side on at the molecule directly down that bond. The way we think about it is imagine taking a paper disc and putting it in that bond between the carbon on the left and the carbon on the right. That is what this circle represents. This circle represents an imaginary disc slid between this bond, separating the carbon on the left from the carbon on the right. And when I do that, notice what happens. If I'm looking at the molecule from the left, one of those carbons is in front of that disc, and one of those carbons is behind that disc. That's what this is representing here. This dot in the middle is our carbon in the front, and we can't see the carbon in the back because it's hidden by that disk. It's still there, we just can't see it. It's hidden by the disk. Okay, we've actually gotten most of the hard work out of the way. We've changed our perspective, we've drawn the template for our new Newman projection. Now we just need to add all of these peripheral groups around this Newman projection to make the same identical molecule, just viewed from a different perspective. To add these 6 groups around the Newman projection, we use these 3 questions as a guide. In fact, once you get good at drawing Newman projections, I have a version of this video that I call the 3-step foolproof plan for drawing Newman projections that relies on these 3 questions. You can check out that video linked down below. We add all 6 groups around the Newman projection. None of the hydrogens are allowed to be implied in a Newman projection like they can be for a line angle structure. Let's start with this CH3 group and we'll walk through the 3 questions to figure out where this group goes in the molecule. First, we'll ask ourselves, is this CH3 group attached to the front carbon or the back carbon? Now, that depends on which side you're looking at the molecule. Right now, we're looking at the molecule from the left, so the CH3 group is attached to the front carbon. Second is that group in the northern or southern hemisphere. If we imagine an equator, write down our molecule, is this CH3 group in the northern hemisphere or the southern hemisphere? It's down in the southern hemisphere, so when we put it on our Newman projection, it will also be down in the southern hemisphere. Now that we've decided it's attached to the front carbon in the southern hemisphere, there's only 3 places it can go. It can go offset to the left, offset to the right, or on the vertical axis of our Newman projection. This can be the hardest part of the Newman projection to figure out, but if you remember that we're looking at the molecule in the plane of the screen, it becomes very much intuitive. Right now, the CH3 group is in the plane of the screen. If I change my perspective so I'm looking at the plane of the screen, it is on that vertical axis of the screen as I'm looking at it from the side. The group isn't coming towards you, it isn't going away from you, it's in that plane, so it is going to be on the vertical axis of our new Newman projection. We can add that group to our Newman projection. The CH3 group is attached to the front carbon in the southern hemisphere on the vertical axis, so it's a bond pointing straight down to that CH3 group. That represents this CH3 group attached to the front carbon in the southern hemisphere. Next, I'm going to jump over to the other CH3 group on the other side of the molecule. We'll go through our same 3 guiding questions. Is this CH3 group attached to the front or the back carbon of our new Newman projection? If I'm looking at it from the left, that disk in the center of the molecule separates the front and the back carbon. This CH3 group is attached to the back carbon. Is this group in the northern or southern hemisphere? If the equator runs across this way, the CH3 group is up in the northern hemisphere of the molecule. It will be up in the northern hemisphere of my new Newman projection. Finally, is it on the left, right, or vertical side of my new Newman projection? If I look at the molecule from the side, that CH3 group is in the plane of the screen. So when I turn to the side, it will be on that vertical axis of my new Newman projection. So this CH3 group will be attached to the back carbon in the northern hemisphere on the vertical axis. How do we draw something attached to the back carbon? Remember, this circle is an imaginary disk separating the front carbon from the back carbon. If I had that imaginary disk there, I can't see the back carbon, and I can't see the bond going all the way to the back carbon. So this is very important. When we draw groups attached to the back carbon, we start at the disk and emanate out from there. That disk physically blocks the front carbon from the back carbon, so if I were really looking at this molecule with the disk, I would only be able to see the top of the bond, but not the entire bond attached to the back carbon. That's how we let the reader know that this group is attached to the back carbon, not the front carbon. The first 2 groups that are in the plane of the original molecule are often the easiest to draw in the new Newman projection. They kind of look like hands on a clock, one pointing towards 12 o'clock, one pointing towards 6 o'clock. They don't always have to be in that orientation, but they are this time. This hands on a clock analogy is actually a really good one, and we'll talk about that later in a separate video when we talk about dihedral angle. Next, let's look at this red hydrogen atom. Same 3 questions. We can start to go a little bit faster through some of these questions. This hydrogen is attached to the front carbon, so it will be bonded to the front carbon. It is up in the northern hemisphere, so it'll have to be up in the northern hemisphere. But let's take a look at the left-right vertical axis. Notice this hydrogen is pointed towards you as the viewer. As you take your position next to the molecule and look at it from the side, notice this hydrogen is now pointed to the right side of your body. This is, again, one of the reasons I love this light board so much. As I stick myself in the plane of the screen, that hydrogen that's coming towards you is now on the right side of my body. When we draw the Newman projection, then, this hydrogen will be on the right side of the new Newman projection. The hydrogen is attached to the front carbon up in the northern hemisphere and off on the right side of this new Newman projection. Let's finish the front carbon and look at the bromine next. The bromine is attached to the front carbon. It's up in the northern hemisphere, so the bromine will be attached to the front carbon up in the northern hemisphere of our Newman projection. This bromine is pointed away from you as the viewer. As you take your position to the side of the molecule and look at it from the new perspective, notice the bromine is now pointed to the left side of your body. The bromine will go on the left side of our new Newman projection. As I rotate that molecule, the bromine is going to take its place on the left side of the new Newman projection. That completes the front carbon. Notice that all 3 groups are offset by 1/3 of a circle, 120 degrees. That has to be true for your Newman projections. They don't have to be in the 6 o'clock, 10 o'clock, and 2 o'clock positions, but they do have to be 120 degrees offset around the circle. If you start having bonds at 90-degree angles or some kind of acute angle, then you're not drawing the Newman projection correctly. Let's finish out the back carbon with the red oxygen and the blue chlorine group. Take a second on your own, pause the video, see if you can place the oxygen and the chlorine on this new Newman projection using the 3 guiding questions we've talked about before. The oxygen, if we're looking at it from the left side, is attached to the back carbon. It's down in the southern hemisphere and is pointed towards you as the viewer. As I look at it from the side, that's going to be pointed to the right side of my body. So the oxygen will be down in the southern hemisphere, attached to the back carbon on the right side of the Newman projection. Notice we stop at the disk to imply that it is attached to the back carbon. I actually have enough information here to figure out where the next group goes. The groups on the back carbon also have to be offset by 120 degrees. So if I have a group at the top 12 o'clock position and the bottom 4 o'clock position, I also need a group at the bottom 8 o'clock position. But let's go ahead and figure it out using our 3 questions. The chlorine is attached to the back carbon in the southern hemisphere, so it'll be attached to the back carbon in the southern hemisphere. It is pointed away from me as the viewer, so as I take my place, it's going to be pointed to the left side of my body. So that chlorine group is going to be pointed to the left side in the bottom back carbon on the southern hemisphere of the molecule. And this completes our Newman projection for this molecule. These molecules are identical. The only thing we've changed is our perspective. Instead of looking at it straight on, we've now changed our perspective and are looking at it from the side to get our new Newman projection. I also mentioned we could look at it from the right side. Go ahead and pause the video, see if you can construct the Newman projection as if we were looking from the right side. Let's think about what changes and what stays the same. Where these groups are around the Newman projection will change because now we've changed our perspective, but the three guiding questions will remain the same. With our new orientation, we now have a new front and back carbon. We still keep the disk between the front and the back carbon, just which carbon is front and back has now changed. Front carbon is still in the front, the back carbon is still in the back, but which carbons those are is different for this Newman projection. Starting with this CH3 group, in the old Newman projection, it was attached to the back carbon. In the new Newman projection, with the new orientation, it's now attached to the front carbon. It's still up in the northern hemisphere, and it's still in the plane of the screen, so when I take my position, it's still going to be in that vertical position on the vertical axis of our molecule. The CH3 group will be attached to the front carbon in the northern hemisphere on the vertical axis. Now that I have this group here, the other two groups will have to go down to the left and down to the right. They have to maintain that 120-degree offset angle. But notice what happens. When I take my position on this side of the molecule, that OH group that's pointed towards you, notice it's now on the left side of my body. So when I draw it in the Newman projection, it will have to be on the left side of the Newman projection. This tracks with our guiding questions. This oxygen group is attached to the front carbon, and it's in the southern hemisphere. When I take my place next to the molecule, that OH group is on the left side of my body. So when I draw the new Newman projection, that OH group will be attached to the front carbon in the southern hemisphere of the molecule on the left side of the molecule. That means the chlorine group will have to go in the bottom right, but let's make sure. This chlorine group is attached to the front carbon and it's in the southern hemisphere. When I stand next to the molecule, that chlorine group is pointed away from me. That means it's now on the right side of my body. So when I draw the Newman projection, that chlorine group will go on the right side in the southern hemisphere attached to the front carbon. Finishing up with the back carbon, this CH3 group is attached to the back carbon in the southern hemisphere. It's in the plane of the original molecule, so it'll be on the vertical axis of our Newman projection, drawn in the southern hemisphere attached to the back carbon. This hydrogen is attached to the back carbon in the northern hemisphere. When I look at it from the right side, that hydrogen group that's pointed towards you will be on the left side of my body. So that hydrogen group will be attached to the back carbon on the left side of the molecule. This bromine group will be attached to the right side of the molecule on that back carbon up in the northern hemisphere. This completes the Newman projection for this molecule, looking at it from the other side. And that's really all there is to it. These three guiding questions will make sure you put the right groups in the right place. Will they always be exactly oriented like this, where everyone is offset one after another around the ring? No, not always, and we'll see examples of that later. But for right now, all we need to do is follow those three guiding questions to make sure you put the 6 groups in the correct place around the Newman projection. These are called staggered Newman projections because every group is offset one after the other around the ring. We can see all 6 groups in the Newman projection with no problem. That won't always be the case. Let's look at this next example to see how the Newman projection changes a little bit. The good news is the process is exactly the same. We're still going to position ourselves in line with that bond, looking down that bond. That's going to make one carbon the front carbon and one carbon the back carbon. We're still going to start with our dot and our disk, with this carbon being the front carbon and the back carbon is the one that we can't see. And we're still going to use our guiding questions to put all 6 groups around the ring. Let's start with this OH group. This OH group is attached to the front carbon and it's in the southern hemisphere. So it'll be in the southern hemisphere attached to that front carbon. Will it be on the left, right, or vertical? If it's in the plane of the screen right now, when I orient myself next to that molecule, it's going to be on that vertical axis. So this OH group will be on the front carbon in the southern hemisphere on the vertical axis of the Newman projection. Moving over to this NH2 group. This NH2 group is attached to the back carbon, so it will be cut off by that disk. We won't be able to see the whole bond. It's in the southern hemisphere, and because it's in the plane, when we look at it from the side, it will again be on that vertical axis. So it will be attached to the back carbon in the southern hemisphere on the vertical axis. It's going to be right behind this OH group. We're not actually going to be able to see it behind this OH group. This OH group should completely block our view of that NH group. It should completely eclipse that NH group like the sun and the moon, so we can't quite see both at the same time. So how do we draw a Newman projection in this fashion? We cheat a little bit. Instead of doing a full 90-degree rotation, we do like an 89-degree rotation, so that bond in the back peeks out just to the side of the bond in the front, so we can still see both of them. It still emanates from the dot, but goes through the disk and emanates out to the side so that we can still see it peeking out next to the OH group. This is assumed to be on the vertical axis. If it really was, we wouldn't be able to see it, so we cheat a little bit and we cheat it off to the side just a little bit so we can still see both groups. Notice again that the bond goes all the way to the center of the disk. If we had continued that bond through the disk, it would go straight to the center of the disk, but it doesn't. It's cut off by the ring. We do not draw 2 parallel vertical lines offset from one another. That wouldn't match. That wouldn't go up to the center of the disk. We need to angle that bond so it would go up to the center of the disk when we do this type of eclipsed Newman projection. Next, we'll look at this hydrogen. It's in the northern hemisphere. It's attached to the front carbon. It's pointed towards you, so when I look at it from the side, it's going to be on your right side, so it will be on the right side of the Newman projection in the northern hemisphere, attached to the front carbon of the Newman projection. The CH3 group is attached to the back carbon in the northern hemisphere. It's also on a wedge. It's also pointed towards you, so it will also be on the right side of the molecule in the northern hemisphere, attached to the back carbon. It's eclipsed by that hydrogen again too. That hydrogen would be right in front of that CH3 group and we wouldn't really be able to see it. So what do? We cheat a little bit again. We set that bond offset starting from the disk as if it were coming from the center of the circle. We cheat that CH3 group just a little bit offset. This still tells the reader they're really in line. They're really fully eclipsed with each other, but we just offset it so we can see both groups. Notice one other thing I did here. With the first group, I offset the back carbon to the clockwise side of the molecule. So I did the same thing with the CH3 group. I offset the back group to the clockwise side of the front group. Do you have to do that? No, but it is consistent, and I like to be consistent. I bet you can tell where these blue groups are going to go. This deuterium is attached to the front carbon. It's in the northern hemisphere. It's pointed away from you, so it will be on the left side of the molecule, and we're attached to the front carbon in the northern hemisphere. The deuterium goes here. Our last group, the fluorine group, is also in the northern hemisphere, also attached to the back carbon. It's also on a dash, so it's also pointed away from you, so it will also be on the left side of the body, so it will also be on the left side of the Newman projection. As you can imagine, completely eclipsed with the deuterium. So we'll cheat that bond a little bit too. Starting from the center of the disk, I'm going to offset it again to the clockwise side of the front group. I'm going to put it right here attached to the back carbon. This again lets the reader know that these really are eclipsed with each other. And that also tells you what kind of Newman projection this is. We call this an eclipsed Newman projection, as opposed to the staggered Newman projection we saw before, where every group was offset one from another. All of the groups in an eclipsed Newman projection are eclipsed. We wouldn't actually be able to see that back group because the front carbon should be blocking it. We cheat the bonds a little bit so we can see them, but all of these groups are completely eclipsed with one another in the eclipsed Newman projection.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further.
Hi, I'm Baby Ninja. Don't forget to like and subscribe.